sit down. I think all the boys got like shunted off to the side.
Yeah, there's more seats up. There's more seats up front if anybody wants to fill in.
You'll hear a lot better up there.
Please have a seat. We're going to start at 8:30. Thank you.
All right, welcome everyone. Welcome to New Jersey Astronomical Association. My name is Mike. I'm the recording secretary here. And tonight we have a very special guest, Dr. Jessie Christiansen. Dr. Christiansen is a very accomplished astronomer and astrophysicist, and she is chief scientist at the NASA Exoplanet Science Institute at Caltech. She also won the 2018 NASA Exceptional Engineering Achievement Medal for her work on the Kepler planet sample. She has published multiple discoveries and co-authored multiple papers on exoplanets. And you also may have seen her on the show How the Universe Works, if you're watching that. So with that, I'll turn it over to Dr. Christiansen. Welcome.
Thank you. Thank you, Mike. Hi, everybody. Thank you so much for coming out tonight. It's really great to see everyone. So as Mike said, normally I'm at Caltech, which is in Los Angeles in California, but my husband and I are spending a sabbatical at Princeton, just down the road. And one of the things I really enjoy doing is giving public talks on astronomy. So I reached out to the New Jersey Astronomical Association and was like, I'm here. And they were like, oh, yeah, come give a talk. So that's why I'm in front of you today. So as Mike said, I'm the chief scientist of the NASA Exoplanet Science Institute. And we're going to talk a lot more about all of those things. But one of the things I'm going to say at the start and say at the end, we'll start with the children in the audience, but it can go out from there. There's stickers up the front for anyone who wants stickers. They're up the front. And they will still be there at the end. Okay, to situate everyone, let's get everyone on the same plane of knowledge. What is an exoplanet? So I'm at the NASA Exoplanet Science Institute. Okay, here is a schematic of our solar system. I'm really enjoying how it like bleeds into the mural on the wall over here. So this is the sun. We have one star in our solar system. That's not always true. Other solar systems have more than one star. We have one, kind of boring. We have 8 planets. Boo, hiss. I know, I'm sorry. I wasn't there when they voted Pluto out. It's not my fault. So we have one star, we have 8 planets, we have dwarf planets. So really guys, you should not feel bad about Pluto. It went from being the worst planet to the best dwarf planet, king of the dwarf planets. So it gets its whole own bucket, very exciting. And the reason we made this new bucket is we started to find all of these other things in the outer solar system that looked like Pluto. And they looked much more like Pluto than they did the rest of the planets. So now we have planets and dwarf planets. Okay, we also have minor planets, which is basically everything else in the solar system that we've been able to catalogue that's bigger than a grain of dust. Space is really big and really empty, and we've found over 1 million things in our solar system. Asteroids, Trojans, centaurs, all these different types of things. But what's an exoplanet? An exoplanet is a planet around another star that's not our sun. So our sky, hopefully you get to see it tonight outside, is full of stars, thousands of stars. And for a really long time, I'll go through a little bit of the history, we've wondered if those stars have planets. But it's only in the last few decades that we've actually discovered they do. Turns out planets are everywhere, which is really brilliant. So those are exoplanets, planets around other stars. Okay, so let's get back to this history, this story. It's one of humanity's oldest questions. Are we alone? You know, tens of thousands of years ago in our prehistory, people were sitting around fires, looking up at the sky and trying to think about the cosmology. They were trying to come up with stories to explain where we came from. Why are we here? Are we alone? So 600 BC, which is about 2,500 years ago, the Greek philosophers, so Plato, Aristotle, Socrates, they were talking about this idea. So we've moved from prehistory to now just ancient history, of whether there was only one Earth, whether Earths were singular or multiple. And actually, Plato and Aristotle argued that there was only one Earth. There could be no other Earths. Earth was unique. So that was one position 2,500 years ago. We're going to jump forward a couple thousand years into the future, but still in our past, 1592, the Renaissance. In Western art and music and literature and science, this is an incredible period. Ideas are exploding all over Western Europe. And here's a thought that I really enjoy. This is an Italian mathematician. Thank you. There we go. There's an Italian mathematician. His name is Giordano Bruno, and he says this. There are countless suns and countless Earths, all rotating around their suns in exactly the same way as the 7 planets of our system. I know there's a lot of amateur astronomers in the audience. I will leave it as an exercise to the reader, which are the 7 planets they're talking about in 1592. Okay, so Giordano Bruno has this idea. There's as many planets as there are stars. And in the rest of this quote, he also says the problem. The problem is stars are very big and bright. Look at this wall over here. Everybody look to your right. This wall of stars, they're huge, they're bright. And planets are really small, relatively speaking, really small. And they're not putting off watts and watts and watts of energy, right? They're very small and they're very faint. So it's just really hard to find them. Unfortunately, I will say, he did get burned at the stake in 1600, in no small part because of this idea. It was the Renaissance, but it was also a time where the Roman Church had a lot of sway in Italy, and this was heresy, because this was against the word of the Bible, right? The Bible said a very specific thing about Earth that this was against. So he also said a bunch of other stupid things about the church at a time where you shouldn't. But one of the reasons he got burned at the stake was claiming the plurality of worlds. Okay, so we have this idea. They're everywhere, but they're really hard to find. Let's jump forward another 400 years to 1952. An astronomer, Otto Struve, thinks about it for a while. And he's like, how would we find these things? And so he proposes this idea. One of the things they knew in 1952 was how to find binary stars, 2 stars orbiting each other. And what you could do is if you looked at the stars, you could see their velocities were going back and forth as they went around each other. And so Otto Struve was like, okay, what if you took out one star and put a planet in instead? The star would still wobble due to the gravitational pull of the planet. It would just be a really tiny wobble relative to what we could see. So he's like, if we just had a good enough spectrograph, we could measure this. At the time, everyone was like, that's crazy. We'll never have precision that good. We'll never find planets that look like that. 40 years later, in 1995, the first planet was found, 51 Pegasi b, orbiting a sun-like star using this method that Otto Struve proposed. And just a few years ago, that was awarded the Nobel Prize. The 2019 Nobel Prize went to this discovery of exoplanets using this technique that Otto Struve had come up. So in a few thousand years, which astronomically speaking is very fast, we've gone from just this idea, right, just thinking about it and being like, do planets exist, to trying to come up with how do we find them, to 40 years later actually able to execute that. Since then, we've found more planets. I forgot to check if sound will work. Should I just try and see if sound works? All right, we're going to press play. There might be sound. Okay, the year is going up. Every time you hear a tone, a planet's been found. The color is by the different technique. The tone is by how short a period the planet is, how fast it's going around its star. So Mercury would have a very high tone and Saturn would have a very low tone. So this is when I start my PhD, 2004. So they're only about 100. In 2009, the NASA Kepler mission launches, and where Kepler starts finding planets in one part of the sky will really start to pop out. It's here. So this is the footprint of the Kepler telescope, which you can see very clearly. In 2013, there was a hardware error on the spacecraft, and we weren't able to keep looking at that field. But we could look at the ecliptic. So this is the ecliptic. So we're marching through. And this video was made 2 years ago by NASA to celebrate hitting 5,000 known planets around other stars. So we went from none to finding one in 1995 to 25 years later, we have over 5,000. So, what do we know about the planets we found so far? This is the only plot that's going to appear, and I'm going to walk you through it. It's going to be okay. All right. So on this axis, I'm showing the orbital period of the planet. So what's the orbital period of Earth? 365 days. So 365 days is out here. On this axis, I'm showing how big the planet is relative to Earth. So Earth is here at 1. So if you go 1 out to 365 days, this is the Earth. So who can guess what these are? Yeah, they're the other planets in our solar system: Mercury, Venus, Earth, and Mars. So that's what we found. So up until the launch of Kepler, had we found anything that looked like the planets of our solar system? No, we'd found these huge planets. So Jupiter is 11 times the size of Earth. And so this is 1 day, 2 days, 3 days, 4 days. We'd found a whole bunch of Jupiters that orbited their star in just a few days. This was 51 Peg is one of these. This was the first type of planet we found around another star. Now, they're so close to their star that these are Jupiter-sized planets heated up to thousands of degrees. So they're called hot Jupiters because astronomers shouldn't be allowed to name anything. But this was a whole amazing new class of planets that was discovered called hot Jupiters. But they're nothing like the planets of our solar system, right? And then Kepler launches, and this is what the picture looks like now. So we have found thousands of planets in between hot Jupiters and our solar system. But what have we not found yet? Planets like the planets in our solar system. Which brings us back to the title of this talk, The Search for Earth 2.0. So finding planets is very exciting. I've spent my whole career doing it. It's a lot of fun, I'll say that. But honestly, one of the things that drives me and many of the people who do this is specifically searching for Earth 2.0, right? What makes Earth Earth? What makes Earth capable of hosting life? It's rocky, so it has a solid surface that water can gather on, lakes, tide pools, oceans. So rocky might be something that we need. The right temperature for water to be liquid on the surface, right? Venus is too hot, Mars is too cold, Earth is just right. So we call it the Goldilocks zone. And the other thing, which might be important, we're still trying to work this out, is the sun being a boring middle-aged G-star. A G-star is just the name of that type of star. What does it mean that this Earth is orbiting a star like the sun, as compared to all of the other stars in the sky? Most of the stars in the sky are smaller and cooler than our sun. So what does it mean that we orbit something like the sun? So when we say the search for Earth 2.0, that's what we're looking for. A rocky planet in the habitable zone, or the Goldilocks zone, of a star like the sun. Okay? So that's what people be like, what do you mean by Earth-like? That's what I mean by Earth-like. Okay, so we've talked a little bit about the Kepler mission. So the Kepler mission was launched in 2009, and it had one goal. NASA spent $600 million to answer one question, which is how common are Earth-like planets, rocky planets in the habitable zones of sun-like stars. So it was a 1-meter optical telescope, which is down here, and it stared at that one patch of sky that I showed you in that video for 4 years. And it used a very, very basic form of measurement. This is the footprint on the sky. So for the amateur astronomers out there, this is Cygnus and Lyra, so it's between Cygnus and Lyra. So in that patch of sky, next time you go out in the summer and look up, we know of thousands of planets in this tiny patch of sky. So the method that we use to find is called the transit method. So let me play this. This is an animation. This is not a real observation. This is an animation of a very small, cool red star called TRAPPIST-1. And TRAPPIST-1 has 7 rocky planets around it. Now, normally, if this was how the system was arranged, you wouldn't be able to see anything. But luckily for us, it's not arranged that way. It's lined up perfectly, so all 7 of those planets pass between us and the star. What that means is, if you measure the brightness of the star over and over again, you see dips. You see dips over and over again. Every time a planet passes in front, dip. Now, this is just measuring the brightness of the star. It's very, very basic, but you can learn a lot about the planets just from this. One is the length of time between 2 consecutive dips that look the same. Now, obviously, in a light curve like this, there's a lot happening, so it's hard to pick out. But for instance, B, this is the closest in planet. This is transiting every 1.5 days. That's how close it is to the sun, to its star, to its sun. So the time between two transits tells you the year, tells you the orbital year. If you lived on B, you'd have a birthday every 1.5 days. The depth of the dip, how deep this is directly related to how big the planet is. Bigger planets block more light, and smaller planets block less light. So then you can start to talk about the size, the density, the composition. So for instance, with TRAPPIST-1, we know that they're all rocky planets because they're so small. So that's how the transit method works. Okay, all right. So Kepler's goal, operated for 4 years. How many planets are like the Earth? Did we achieve our goal? 0 planets like the Earth. So where this huge glut of planets that we found falls off, this lower envelope here, that's exactly where the sensitivity of the spacecraft falls off. So it's not that we don't think there are rocky planets. It's just we ran out of our ability to sense them. If anyone's particularly interested in the details, come and ask me afterwards what we did wrong, because we did something wrong. But we weren't able to get there. So this question remains. We don't know the answer yet of if there are Earth-like planets out there, and if there are, how common they are. We can make some guesses based on these are super common, right? Turns out we found thousands of planets here. So we don't have a good reason to think that they suddenly fall off. So if you extrapolate, which is something that you should never do, but scientists given an underdense space of data will extrapolate. If you extrapolate, we think that Earth-like planets are common, which is pretty exciting. But that's based on extrapolation. So we don't know yet, but we think that Earth-like planets are probably common. So what have we found? So this is an animation of a planet called Kepler 452b. This was the most Earth-like planet that Kepler found. It's got a period of about 370 days, which is pretty close to 365. It's orbiting a star just like the sun, so that means it's the right temperature. It's about 1.5 times the size of the Earth, and that's where we start to get a little worried that it's not a rock with a thin atmosphere anymore, but starts to have a deeper and deeper atmosphere like Uranus and Neptune. So, you know, it could be a rocky planet. Maybe it's a mini Neptune, but maybe it's just a super Earth, we call them, because that's how you get funding. So it's either a super Earth or a mini Neptune. If it's a super Earth, maybe it's habitable. The main problem with Kepler 452b is that it might not be there. The signal that we found in the data could be a planet, or it could be noise. It looks just like the noise that we see elsewhere in the data. This time that the noise just happened to line up 3 times, which is suggestive that it's something truly repeatable. But again, we don't know. So Kepler 452b is as close as we got. Now, I've talked a lot about the fact that the sun being this G star, this boring middle-aged yellow star, might be important, but it might not. What we have found is a bunch of rocky planets in the habitable zones of M dwarfs, red dwarfs. So 75% of the stars in the galaxy, there's 100 billion stars in the galaxy, 75% are M dwarfs. They're half the size of the sun or less, they're thousands of degrees cooler, they're much smaller. Which means their habitable zones, their Goldilocks zones, are much closer, right? If you imagine like a bonfire on a beach, at the start of the night, you have to stand back because it's really hot. But as it cools down, you kind of huddle closer, right, to stay at the same temperature. So the habitable zones of M stars are much closer in. That just means it's easier to find the planets by transit because they transit more often. So we found a bunch of these. This is an artist's impression of a really exciting rocky planet in the habitable zone of an M dwarf. This is Proxima Centauri. That's the closest star to us. If you leave the solar system and start going, the first star you hit is Proxima Centauri. It's about 3.8 light years away. So if you were in the neighborhood and you're going to go borrow a cup of sugar, it's Proxima Centauri. It has an Earth-like planet. It has a rocky planet in the habitable zone. That's so cool. And I haven't added it yet, but last week, did you guys hear? Barnard's star has a rocky planet around it. Barnard's star is the second closest star system to us. So this is Alpha Centauri A and B, and Proxima Centauri. That's a triple star system. If you keep going, the next neighbor down the street is Barnard's star, and it has a rocky planet. They just announced it last week. So exciting. So one of my jobs is I'm the lead scientist of the NASA Exoplanet Archive, which is how NASA keeps track of all the planets we found. So it's a big deal for me when a new planet gets announced. Yeah. So we like rushed out a release on Tuesday, and it was very exciting. Anyway, okay. So what's the problem? Why am I not more excited about this? The problem is that M dwarfs have a very different radiation profile than the sun. The sun puts out most of its energy in the middle of the optical. It's a bright, white star. Most of it's coming out the yellow, the green. Life on Earth is optimized for this beautiful, lovely wavelength of light, which is also pretty stable. Like we just had those cool, did you see the aurora like 2 nights ago? Okay, that's because the sun burped, right? Normally the sun, pretty stable, pretty chill. Very occasionally, especially at this time in its cycle, it'll burp. And so that's pretty, but it can also be dangerous, right? If it does too big of a burp, bad things happen. Communication satellites go down. It's not good. M stars burp all the time. It's like they have gastro, right? This is bad. Also, a much higher fraction of their radiation comes out as high energy radiation, so X-rays and UV, right? So UV, I'm from Australia. This is why we invented sunscreen. X-rays, that's why the dentist makes you wear the lead apron when you're getting an X-ray, because it's bad, right? We use UV to sterilize equipment on Earth. So if you're a rocky planet right next to a star that's putting out a lot of UV, maybe it's not good. So we don't actually know yet. This is an open question that's being really actively studied right now of whether these planets are actually habitable, right? They get so much high energy radiation. Maybe they're covered in tardigrades. We don't know. Maybe everybody there has superpowers from the high energy, right? You guys know the story of Superman? The reason he has superpowers on Earth is because our sun looks different from his sun, which is a red dwarf. I just love it when they include science in science fiction. Anyway, so we have found something like 14 rocky planets in the habitable zones of red dwarfs. That could be cool. We just don't know yet whether it's cool. So in terms of truly Earth-like, we don't have anything yet. So when I say that right now we're working very hard on this question of whether these planets around M dwarfs are habitable, this is an animation of NASA's James Webb Space Telescope. So this launched a couple of years ago. It was a 6-meter telescope that unfolded in space. We launched it all folded up, and then it went out and then unfolded like this. It was terrifying. Every astronomer in the world just sat there for like 7 days, just like, it was really very scary. Because so many moving parts had to work, and it was, halfway out into space. There was no way to fix anything if anything went wrong. It's working, guys. It's working so great. Anyway, so it's a 6.5 meter telescope in space. So what it can do is look at these planets and see, do they still have atmospheres? Do they have liquid water? Do they have biosignatures? So biosignatures is just a fancy word for signs of life. So that's what James Webb is doing right now on a bunch of these rocky planets in the habitable zones of M dwarfs. Okay. So we haven't found Earth 2.0 yet. We found a lot of really cool stuff on the way. All right. So one of the things we found was these hot Jupiters, which I said, but the more we find, the more detail we're able to study them in. This is an animation of a hot Jupiter called HD 1897333b. I'm sorry, they have terrible names. They have such cool ideas, and then we give them these nonsense names. HD 1897333b is a hot Jupiter that's orbiting very, very close to its star. So you just got to see the star burp. And what we can see when the star burps is this huge atmosphere gets stripped away from the planet. So this planet is so close and so bright, we've been able to measure the atmosphere temperature, the atmosphere composition, and the atmosphere wind speed, which means we've been able to say on this planet, it's raining liquid glass sideways at 2 kilometers a second all the time. So not a vacation destination, just a really cool, exciting planet. This is the sort of thing we're able to learn about these planets. Okay. So these planets down here are the same size as Earth. These are rocky planets, but they orbit their star. This is one day. They orbit their star in less than a day. Hours. Just they go around in hours. So if they're that close to the star, they're thousands of degrees. What happens to rock when you heat it up to thousands of degrees? It melts. These are lava worlds. We actually think that like a full side of this planet is just melted to a big magma ocean. So this is an animation of a system called Kepler 10. So this is the star and this is the rocky planet that orbits it in just less than a day. If anyone gets real seasick, I'll tell you when to look, because it's gonna get wild. You know, NASA animators don't have a lot to work with for exoplanets because you saw the light curve, right? It's just a bunch of points. So when they get asked to make stuff up, they really go to town. So this is an example, right, of this like magma ocean facing the star. And you can see as it cools to the night side of the planet. So these planets are so close, they're tidally locked, the way the moon is tidally locked to us. You know how we always see the same side of the moon? So these planets would be the same. One side of the planet would always face the star, and one planet would be faced away. So it's so close that it's like, silicates are just getting stripped off the surface. This is this kind of like silicate rain that we're falling through. And this is pure fantasy. This is just what would it be like to be flying across the surface of a magma planet? So again, if you get seasick, look away. I'll tell you when to look back. We're gonna go for a fly. They need some real like, you know, John Williams music here or something. All right. Look away now if you get seasick. We're about to dive. Again, they don't have a lot to work with, so they just, when they get given a cool thing. So lava worlds. We have lava worlds, people. That's super cool. We have found a bunch of rocky planets that aren't the right temperature, but they are kind of like Mercury-Venus analogs, right? Like these are kind of Mercury-Venus analogs. And we have found a bunch of ocean worlds and ice giants that look like, you know, Neptunes and Uranuses and bigger. But actually, the big mystery is what are these thousands of planets in here? Now, in our solar system, this is, here. This is Jupiter, Saturn, Uranus, and Neptune. This is their sizes relative to each other. This is Earth. Earth is 4 times smaller than Neptune. And then we have Venus, Mars, and Mercury. So that's kind of the size distribution. So in our solar system, there's a really big gap between the little rocky planets and the giants, right? There's the ice giants and then the gas giants. There's this big gap. Most of the planets we've found so far, a goodly fraction, are in between. They're bigger than Earth and smaller than Neptune. And that's why there's this mystery where I was saying before, like we don't know whether they're mini Neptunes, like if you took an ice giant and scaled it down, or if they're big Earths, so you take a rocky planet and scale it up. Or maybe they're just another type of planet that we don't have an example of in our solar system. And one idea is water worlds, where like 50% of the planet's mass is water, so an incredibly deep water ocean. Actually, the first one we found in this size range is nicknamed Kevin, after Kevin Costner from Waterworld. Some of them do have nicknames, which is a lot of fun. But so we don't know what these are yet. But it's fun to think about. Okay, so I made that point at the start that our sun is a single star. Now, most of the planets we found so far have been around single stars, but that's more a function of where we're looking than in reality. This is a classic scene that hopefully people remember. It's Luke Skywalker on his homeworld Tatooine, and you see this binary sunset in the background. This was in the 70s. Like, George Lucas in the 70s is like, what if there were 2 suns? And guess what? We've found planets around multi-star systems. So this is a system that has 3 planets around it, and they're all orbiting 2 stars at the center. And so one thing I like is, like, he even got the colors right in the 70s. Like, he just predicted this system would exist, which is super cool. One type of system we found, so this is going to start to get really esoteric and maybe a bit depressing. In about 5 billion years, our sun will expand. It'll become a red giant. That'll be pretty cool. We won't be here, but it'll be pretty cool. And then those upper layers of the sun will puff off and become a beautiful planetary nebula, which again will be very cool, but we won't be here. And what will be left behind in the middle is a white dwarf, just a cooling chunk of carbon and oxygen that'll just slowly cool forever. That's like the end stage of our sun. And there's been a long time question, can planets survive this? Can planets survive this red giant planetary nebula white dwarf phase? And one of the things we found is planets around white dwarfs. So some planets either survive, or there's a second generation of planets that gets reconstituted after this, after the solar system goes through its whole change of life. So yeah, we have found planets around white dwarfs. So when we think of our solar system in 5 billion years, it's not all doom and gloom. Maybe planets survive. Okay, this is the animation I showed before, but I'm going to add a piece of information now. So this is TRAPPIST-1, 7 rocky planets. The orbital period of the longest planet is 19 days. That's 7 planets all orbiting into the star, around the star, with periods of less than 19 days. So Mercury in our solar system has a period of like 88 days. This is 7 planets inside like a quarter of the period of Mercury. So one of the things we found are incredibly packed systems where there are as many planets around this star as you could fit and still be stable, which is very cool. And my favorite example of these is called K2138. It's my favorite because it was found by citizen scientists. It was found by people at home on their computers looking at Kepler data and saying, hey, that looks like a planet. So a few years ago, it was my job to be the astronomer reading all of these reports, and I was like, hey, that looks like 4 planets. And so we analyzed this system, and there's 5 planets in the inner system and 1 in the outer system. And we'll see if we get the music going. This is the 5-planet system. This is an animation made by Matt Russo at System Sounds. He does amazing sonifications of astronomical phenomena. So you've got the star in the middle, you've got the 5 inner planets. So the tone, again, is the period. So the highest tone is the shortest period, and the lowest tone is the longer period. Every time one of them transits, you hear the note. And the reason it sounds pretty is because this system is in resonance. These periods are all related to each other in very basic ways. For every 3 times this one goes around, this one goes around twice. For every 3 times that one goes around, the next one goes around twice. For every 3 times that one goes around, the next one goes around twice. It's a chain of 3 to 2 resonances. Now, anybody who's studied Western music, the 3 to 2 resonance is the perfect 5th interval, C to G, right? That's one of the most basic fundamental tonic chords in Western music. That's why it sounds nice. This system is playing us Twinkle Twinkle. It's really gorgeous. So if you're interested, this is an ongoing project now using NASA TESS data, which is our current planet hunting mission. If you go to planethunters.org, you can hunt through data and find your own planets, and astronomers will help you get it published. Okay, so here is TESS, which I just mentioned. In 2018, Kepler finally ran out of fuel and wasn't able to keep going. But luckily, we'd already planned for this, and we're launching that year the NASA TESS mission. So this is the Kepler footprint. That's that original field that you've seen a few times. This is one of the TESS cameras, and TESS has 4 cameras. So TESS can do this much of the sky at once. And over the lifetime of the mission, it's actually tiled out the whole sky. And so that was the ecliptic plane survey that I mentioned. That's the original Kepler field. So every tile is 1 month. So it spends 1 year on the southern hemisphere and then 1 year on the northern hemisphere, filling this all in. This was a gap because that's where the Earth was at that time. So where Kepler just looked at that one little patch of sky and found thousands of planets, now TESS is doing the whole sky. And TESS is predicted to find something like 12,000 planets. So more than doubling what we already have. Speaking of Star Wars, the next mission that NASA is going to launch is called the Nancy Grace Roman Space Telescope, which I'm delighted by because it's the first NASA mission named after a woman, which is wonderful. And it will do a planet search. Here, let me get the video playing. So whoever was the animator who made this was very Star Wars influenced. It's either a NASA mission or a Star Destroyer. I don't know. All right, it's coming in. Okay, so this will be a 2.4 meter telescope. It's actually a Hubble spare. You know, Hubble is still operating. So we are launching this in 2 years. And one of the things it's going to do is stare right into the center of the galaxy and look for planets. Now, the center of the galaxy is the densest place we can look for planets, which means that we're expecting to find a lot. So this is the same plot you've seen a bunch of times now. This is distance from the star, but in semi-major axis instead of period, and this is size of the planet. So this is Earth, this is Mercury, Venus, Earth, and Mars. So these were the planets that were found by Kepler, and these are the types of planets that we expect to be found by Roman. The cool thing about Roman is it's sensitive to longer period planets than Kepler was, and for me, the cool thing is that their sensitivities intersect at Earth. So the fact that Kepler didn't find any Earth-like planets, we might be able to fix that with Roman, which, as someone who worked on the Kepler mission, will make me feel better. Roman is expected to find something like 100,000 planets. Now remember, we went from 0 to 5,000 in a few decades. In the next 5 years, we could have, an order and a half magnitude more planets than that, 100,000 planets. And again, as someone who is the lead scientist of the NASA Exoplanet Archive, this is job security. That's what this is. And if this continues and NASA continues to make exoplanet finding a priority, we're on track. If you look at that plot with time, right, that's an exponential. Now, since COVID, I feel like everybody knows what an exponential is. Planets are being discovered at an exponential rate, which is very exciting. Okay. So this is a movie. This is actually not an animation now. This is real data. This is a movie of 4 giant planets orbiting a star called HR 8799. So this is a very nearby star, bright star, where we've been able to block out the light from the middle. That little animation, that little figure of a star is where the star would be. We've been able to block out the light and search for planets. Now, this is state of the art. This is so cool. We're making movies of planets around other stars. But these are giant planets. They're actually super Jupiters, because that's how you get funding. They're big planets. And you can just barely see them, right? That's a super Jupiter. So you can't see an Earth yet. So it's almost like we're back where the Greeks were 2,500 years ago. We have this idea. We think that Earth-like planets are out there, but we don't have the technology. We can't do it yet. But this time, we have a plan. We have a plan. So the plan is called the Habitable Worlds Observatory. So this is NASA's exoplanet roadmap over the last few decades. So Hubble, we mentioned. There's Kepler K2, which ran out of fuel. TESS is the one that's launching right now. JWST, we talked about, is characterizing the atmospheres. Roman is the one that's going to launch in 2 years and find 100,000 planets. The one after that is called Habitable Worlds Observatory. Now, this is how NASA wants to make that movie, but for Earth-like planets. So this is 20 years from now. 20 years from now, we hope to launch this. It's going to be something like a 6-meter telescope, so kind of like JWST, but designed specifically for direct imaging. A 6-meter telescope whose number one goal, remember Kepler, the number one goal will be to image Earth-like planets around other stars. So we have good reason to believe this will happen. So every decade, every 10 years, all of the astronomers in North America sit down and decide, they hash out what are our priorities for the next decade, right? This is actually really useful for funding agencies like NASA and the National Science Foundation, because we can show them this document and be like, all astronomers agree this is the number one priority. And luckily for me, exoplanets, we all got together and decided that the number one priority was Habitable Worlds Observatory. So NASA's moving forward with this, which is very exciting. They started, there's a team called the START, the Science Technology Architecture Review Team, and NASA chose 20 scientists across all of the US to kick this off, and I was lucky enough to be one of them. So I'm really privileged to be on the ground floor of designing this brand new mission that'll launch in 20 years, when some of the kids in the audience are, actually starting their careers. So this is what we can do right now. And again, these are super Jupiters, larger than Jupiter. This is what we want to be able to do. If you put our solar system 30 light years away, this is what we want to be able to see. We want to be able to see the Earth well. If we do it right, we're going to be able to see things like Venus. And then you take that light from that planet and you spread it out and you look for biosignatures. That's the goal. This is a plot showing, oh, sorry, there's one more plot. Dang, I lied. This is a plot showing the spectrum of the Earth with time, basically showing that the modern Earth spectrum looks nothing like the spectrum before life evolved and, complicated multicelled life evolved and oxygenated the atmosphere. So one of the things we have to think about when we're designing this is not what Earth looks like now, but what Earth has looked like for its entire history, which has evolved. If you landed on Earth 4 billion years ago, would you know that there was life? Okay. So this is the goal for NASA 20 years from now, finding an Earth-like planet that we can look at for biosignatures and look for life. So let's say that happens. Let's say the funding works out, NASA continues to get a little bit of money, and we fly this thing. And let's say we find an Earth-like planet. What does that mean? So we have some examples of times where we thought we'd found something pretty cool. This is a suite of headlines from this time. Orson Welles had written this War of the Worlds, and someone read it on the radio. And people tuning into the radio, into the broadcast, did not realize it was a work of fiction that was being read out loud. And there was panic. Everybody lost their minds because, it was a bit of we were being invaded. The story is that we're being invaded. It's War of the Worlds. It's not like Peace of the Worlds, it's War of the Worlds. So this was one time, for instance, when a bunch of people on Earth suddenly thought there was life out there and perhaps it wasn't very friendly. A few years later, we have this. This is the WOW signal. So this is a radio telescope looking for signs of something coherent and intelligent out there. And you can see normally it's 1s and 3s, a 2, a couple of the 6s and 7s get circled, and then this happens. Oh boy, this is a lot. This is a very high energy radio source suddenly appearing and then suddenly disappearing. And then the nightly astronomer whose job it is to flag these things, this is their inscription. Wow! So it's called the WOW signal. Now this one, there was so much excitement, right? Everyone pointed every telescope they had at this patch of sky to be like, what was it? Is it happening again? Even now, decades later, there was just recently a GoFundMe to get more money together and do another search of this patch of sky. This is a super interesting signal and one of the most promising things we've had so far. So this one engendered excitement and enthusiasm and money. So these are just different examples of how people have reacted. So now we can just get speculative, right? How would we react if we found an Earth-like planet? How would government funding change, right? The US budget has a lot of defense. Would that go up? If we suddenly found life on another planet? What would change? What would change about our priorities, now government's priorities? What would change about religion, right? So I mentioned tens of thousands of years ago, we would all sit around the campfire and try and think about cosmology, look at the sky and try and work out what the truth was, what was the underlying story behind us, what was our story. If we found life on other planets, what would that do to all of the stories we've told ourselves for thousands of years? How would it change? Would it just get folded in or would it get rejected? So, for instance, Isaac Newton. Isaac Newton was very religious. He was an incredibly religious man. He was totally on board with the idea of other planets, and he was just like, God is omnipotent. God is just God of all the planets. There's no problem. There's one planet, there's God, there's many planets, there's God of many planets. It's fine. So there are different reactions that religions would have to this idea of life on other planets. Hopefully we're past, burning people at the stake, but I can't guarantee it. Okay. What would it change about conservation, right? So we are barreling towards a climate catastrophe on Earth. In 100 years, parts of the Earth will be uninhabitable that were habitable before. When I give this talk to people, often folks are like, well, if we find an Earth-like planet, can we go there? Is it an escape route? Is it plan B? It's not plan B. It's not plan B. Even if there was an Earth-like planet around Proxima Centauri, which there is, we are not getting there. So unfortunately, nature is cruel and the laws of physics are real strict on this. We are not getting to Proxima Centauri. Really, the only way that we can do interstellar travel that doesn't break the laws of physics is generation ships, right? And that would take 20,000 years to get to Proxima Centauri. So our very, 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 very distant descendants may get there. But this is not an escape route. I'm really excited that we're looking for planets around other stars. This is the one we have. This is the one we need to take care of. But I'm really curious, if we found truly habitable planets, what would that do for conservation? Would it help it or hinder it? And then finally, for individual people, if you woke up tomorrow morning and suddenly knew that there was life on other planets, what would it change about you and the way you picture yourself in the cosmos and the way you picture us as a civilization in the cosmos? So I will leave you with that question. What would it mean to you? Thank you so much. This is the podcast that I host out of Caltech about discovering exoplanets. So if you're interested in hearing me talk at all more about planets, there's a bunch of episodes up here, and there's a bunch of stickers at the front for the show. So stickers, podcast, QR code. The QR code is also on the stickers.
Before everybody leaves, thank you very much for a wonderful talk. Very
Yes.
informative. We love your enthusiasm, your passion. It's great that you're here. You know, we Zoom a lot, but it's wonderful to have a speaker here with your credentials. So
Yeah, no, again, it was lovely to come. Thank you so much. And if you have questions, let me know. Yes?
And I've heard of deep biospheres before. For example, below Europa,
Mm-hmm.
there's a lot of research right now. Is it possible that life can exist on planets that they're inhabitable on the surface?
For sure.
Is that something that NASA is looking into?
Can you repeat?
Oh, yes. So the question is, there's a lot of active research in our solar system about deep biospheres, so looking in the oceans of icy moons like Europa and Enceladus. Is NASA thinking about that for exoplanets? So hopefully in 2 days, we're going to launch Europa Clipper, which is going to go to Europa and fly through the plumes that are coming off the ice to look for biosignatures. For exoplanets, we're still just barely at the point of being able to find them, let alone look subsurface. So for right now, like for the next 20 years, NASA's focus is on looking for planets with atmospheres that we can look at, because you can see an atmosphere, but you can't see deep into the underneath. But there's a lot of work that people are doing on the interaction between atmospheres and surfaces and subsurfaces. So if you looked at an atmosphere and saw this chemical, what would it tell you about what was happening in the interior of the planet? That's really exciting, because it's kind of a secret way to get in and look underneath.
Right. And also, can you go back to the plots of archaic Earth?
Yeah. The second plot that I snuck in. Yeah.
And then, what do all these lines mean?
Yeah, sure. So this is as a function of the wavelength of the light. So light has a bunch of different colors. So as a bunch of different colors of light, how reflective the planet was. So in some wavelengths, the planet is not very reflective, and that tells us something about the molecules that make up the atmosphere. So like water is an absorber at 1.4. So at 1.4, we're not very reflective, because water in the clouds and the atmosphere is absorbing all of that light. But at 1.5, water's reflective. So if you look at a planet in different colors, you'll see different things. And that tells you something about the molecules, because the molecules change the planet at different colors.
Oh, and one more thing. In white dwarf planets, wouldn't the previous red giant explosion incinerate all the planets?
Well, that's what we thought. But now we found planets really close to white dwarfs. So now there's this whole question of, like, did they migrate in after the red giant phase? Did they somehow survive this common envelope? Like, were they just like inside the puffy red giant outer atmosphere and survive? We don't know. But it's really surprising that we found so many planets so close to white dwarfs, and that's something we're trying to work out right now.
But then what if the planet still exists? Maybe only the surface is incinerated.
Maybe.
Maybe the surface is blown away and reveals a perfectly thriving biosphere.
We don't know. Not yet. Questions?
For the graphs, you had like the radius of the planets found and the periods of planets found.
Yes.
What about like the stars, the planets in the binary system? Because like the period is like the system is chaotic. How do you determine the period?
Yeah, so you find an average period basically around the center of mass of the system. So the binary will have a center of mass. And the tricky part of finding circumbinary planets is they're not periodic, right? So the software that we write to search for these signals is looking for periodic signals. So it's hard to find these because they don't happen periodically. So most of them have been found by hand, by people looking at the light curves of binary stars. And then you just find an average around the center of mass.
Sorry,
Oh, sorry. Go ahead.
it's a related question. How do they orbit the binary?
So there's two ways that planets survive in binary systems. One is that the stars are so close and the planet is so far away that the planet can kind of treat it like a point mass, like they're in this gravitational well and you're orbiting around it. The other is that the stars are so far apart, which is like Alpha Centauri and Proxima Centauri. Like Alpha Centauri A and B are over here and Proxima Centauri is over here, and the planet's like this. So then the stars are so far apart that the planet can just go around one and basically ignore the other. We don't see any stable, complicated like horseshoe or figure eight or anything like that. They're always quite far away from whatever the gravitational interaction of the two stars is. Oh, sorry, in the back, yep.
So you mentioned that like test data is coming in and then other satellites also. Are those also detecting exoplanets via transits? And if so, what potential planets are we missing by like putting all of our eggs in like the transit basket?
Yeah. So we're focusing a lot on transit. So yes, TESS uses transit. Roman will use microlensing and transit. Microlensing is another technique I didn't talk about. And then habitable worlds, we use direct imaging, which is the one where we block out the light. But you're right. So sorry, I should have repeated the question. If we're only concentrating on transits, what are we missing? Remember I said we only see it transit if it's lined up just right. So most planetary systems don't transit. So that's why when you do a survey like Kepler, you have to look at 200,000 stars to find the 2,000 that are lined up just right. Now, for right now, it's just a cheap and easy way to do it, right? But that's why we're spending the money to develop habitable worlds, because that's direct imaging, and then it doesn't matter as much how the planetary system is aligned on the sky, as long as at some point the planet gets far enough separated from the star that you can see it. So you can come up with like pathological cases where the planet has a very eccentric orbit, like along the line of sight, and then it never gets very far away. But most of the time, you'll be able to see it. But it's really interesting because we're kind of trapped right now in a technique that is limited by funding, but in 100 years we know that won't be true. So there are some people who are, for instance, like, we should look at the planets that can see us transit to see if they're sending us messages, right? Because they know we're transiting and we know they're transiting, and that's interesting information. It's like, this is only like the 2 decades where that matters, right? Like in 100 years it won't matter that we're transiting and they're transiting. They might be well past that, right? So we get stuck in this transit bucket a lot, and I agree it's annoying, but right now it's just the reality of the funding, right? It's the cheapest way to find planets. You can do it on the ground with a 10-centimeter telescope.
For the exoplanets we found, are their orbits more circular or more elliptical, and does the Kepler's third law apply?
Yes, so Kepler's third law, as far as we can tell, always works. It's a mix. We find some circular and some eccentric. Especially the hot Jupiters are circular and the cooler Jupiters are often eccentric. All right, why don't I let people go, and then if you have questions, you can come up, because I want to make sure people get out to the telescopes and everything. Thank you so much.
Before everybody takes off, we are the New Jersey Astronomical Association. Thank you for being here. We're a nonprofit organization. We appreciate your support. There's a donation box in the back, but also on the back counter there's some postcards that you can put on your fridge, QR code on the back that'll take you to our website. We would like to have more members join us so we can continue doing the things that we're doing right here. And it's just wonderful listening to this young gentleman ask these questions to an astrophysicist. It's like, doesn't get any better than this, right? And that's what it's all about. So thank you very much. If you go out, we're going to break up in a couple pieces. If you go out the back, I don't know if you can, somebody, who's back there? Keith, could you manage some people to go upstairs?
Yes.
And then people to go up?